Hello, everyone, and welcome. We're going to get started and just wait a couple of minutes before we start to allow stragglers to come in. I hope everyone can hear me. So just while we're waiting for the last few people to come in, I'm going to just play our little marketing video for the PCM Slugger. This video was produced about 4 years ago when we named the PCM Slugger with that new name. So it's not a new video, but I'm just going to play that while we're waiting for the last few people to come in. And once that video is done, we'll get started. Again, there's nothing new or special about this video. But I'll just play this. Oh. Sure if you have the sound or not, but it doesn't really matter. There's no text over, it's just some music in the background. Okay, you'll have to excuse me. I have a bit of a cold, so my voice isn't where it should be. But we get started on the presentation here. Just a quick introduction to our presenters today. My name is Paul Skoczylas. I've been at PCM for about 4 years. Prior to that, I was in Canada working at a research company there, so I might have run into some people there in the past. But I've been doing PCP training for a long time, 25 years or something like that. So I've been all over the place and seen lots of different things, and hope to share some of that knowledge with you. Today we're talking specifically, of course, about one PCM product, but I hope we're going to give a good technical background to it. So that's a little bit about me. Pat, if you want to introduce yourself real quick.
Hi, I'm Pat. I work out of Lloyd here in Alberta, and I've been on both the producer and the product side of business since 1980. So got quite a few years moving these, and for the last 2 or 3 years, we've been moving a few sluggers and having some pretty good success.
Okay, good, thanks. So on the screen, you should see the title slide, I hope. I don't know if anyone can give me a thumbs up or something just to you can hear us and see the screen. Anyone? Okay, good, thanks. I see a thumbs up. Perfect. We're gonna wait. We're gonna do our. If there's any questions, we'll do them at the end. Ryan, you put your hand up. I'm not sure if that was supposed to be a thumbs up or not. We're gonna save any questions till the end. So we're gonna go through the presentation and then we'll do question and answers at the end. So please keep your microphone muted until we get to the end and you want to ask a question. So we'll get to that at the end of the presentation. Sorry, just let me bring up my presentation page again here. Is this working? There it is. Okay. So just a quick note, you'll see on that video you saw HR PCP and it's on the slide here. That was the generic name that we use and we still use when we're doing like an SPE paper or something like that where we're not allowed to use trade names. So HR PCP, the hydraulic regulated progressive cavity pump, it's just a descriptive name. The trade name we have on that, which that video was introducing about the last 4 years or so, we've been calling this the PCM Slugger. So Slugger HRPCP, same thing. Slugger is just the trade name for it, and whereas HRPCP is just a generic descriptive name. Moving on. Purpose of the PCM Slugger is to improve the run life in multi-phase wells. So that's the bottom line. That's what we're aiming for. That's what we believe it does. It's patented and proven. It's been around for a while now. It's a simple upgrade to any of our PCM pumps, any of the elastomeric PCM pumps. Very simple upgrade to that. And we can use it anywhere where you use another elastomeric PCP. No downsides to that. Anywhere you've got viscous oil or solids, anywhere where you use a PCP, you can use a Slugger. The reason you put the Slugger on is when there's gas in the well, or even if there might be gas in the well, a lot of gas going through the pump. Gas reduces the run life. We'll talk about that in just on some of these later slides. And the Slugger is intended to improve the run life when there may be gas going through the pump, or is gas going through the pump. It reduces the stress in the elastomer. It reduces the hysteretic heating. Together, that gives you longer run life. So we'll go into that and over the next few slides. But also, like I said, it pumps the solids, viscous oil, just as well as a standard PCP. There's really no downside to this technology. I don't know if you've ever seen one of these rotors. They basically it has these flat spots milled onto the rotor. So these are, sorry, just admit somebody here. These are the hydraulic regulators. The sizing and location of these hydraulic regulators is very carefully engineered. It's not just put a bunch of flat spots on the rotor. Their location and size is the design of the pump and what makes it special. But basically, these provide a controlled leak path from one cavity to another cavity. And the reason for that is to get a more uniform pressure distribution through the pump. So there's just some pictures of it there. It is just that modification on the rotor. So how it works, the top graph here is for a standard non-hydraulically regulated PCP, so the standard pump that everybody has. And you'll find graphs like this have been published by various different companies through the year, not just PCM. I've seen them from our competitors. I've seen them from some universities that are studying these. People have drilled holes along the length of the pump and put pressure gauges in and measured the effect of things like gas going through the pump on the pressure distribution. So with zero gas, you get a nice linear pressure distribution. This is when the pump is fully loaded, has a reasonably high pressure on it. Of course, if the pump is not fully loaded, you might not have pressure coming all the way down the pump. But when it is fully loaded like this, we see with no gas, the blue line, a fairly linear pressure distribution. It's not going to be perfect depending on the pump, but it's the what we normally will see. As you put more and more gas into the pump, so here we have the orange line, the gray line, and then the yellow line, that's with more and more gas, you get a more non-linear pressure distribution. The top of the pump is doing all the work. The pressure gradient in the pump is much higher at the top than it is at the bottom. That high pressure gradient leads to high stress in the rubber. And as the rotor goes back and forth across it, you get this hysteretic heating, this high stress that's cycling, and it really generates this heat inside the elastomer. That high stress, that heat generation together lead to a shorter run life of a PCP, an elastomeric PCP. So with high gas volumes going through the PCP, very, very common we see the pump failing from the top down with a shorter run life. By adding those hydraulic regulators I showed on the previous slide, we get a more linear pressure distribution through the pump. So we're probably not going to get something that looks like the blue line on the top there, but maybe the orange one, where we're getting much more linear pressure distribution. We get rid of that high gradient at the top of the pump with less stress, less internal heating, and longer run life. And the graph in the bottom is just illustrating the temperature measurement. So here, instead of putting pressure gauges in, they put thermocouples inside the pump and measured a standard PCP, the blue line, compared to the hydraulically regulated PCP, or the Slugger being the orange line. And you can see much higher temperatures inside the elastomer with the standard PCP, and the hydraulically regulated pump brings those temperatures down, and that's what gives us the longer run life. Lower stress, lower temperature, longer run life. And the next slide is just showing that same thing. This is the standard slide we have in our marketing materials that showing the same thing. So here we have you can see the little pictures above there that show the red is indicating the high stress in the standard pump with its very high pressure gradient at the top. And the HRPCP or PCM Slugger has lower stress with more uniform pressure distribution. Just some references. This is not new. We've been publishing on this technology for quite some time now, going back to 2004. So I'm just giving you some references here. You can find a lot of these papers should be available on One Petro. You can go on and find them there. Some of the conference papers, excuse me, might be a little more difficult to find, but everything should be out there. The first installation of a PCM Slugger or HRPCP was the first one I found a reference to is Venezuela in 2007, but there may in fact have been one in Indonesia that might have been a little bit earlier than that wasn't referenced in one of these papers. But that's around the timeline we're looking at. That Venezuela installation was described in some of those papers that are shown there, along with some later installations as well. So Venezuela, Argentina, some installations in the Middle East are all described in those papers. And then a couple of summary papers more recently, including the one I did last year, presented in Houston just over a year ago. They included case studies from Australia, where they've actually installed thousands of these pumps in Australia and actually done very well. Some Colombia, and just starting on Canada, which is what we're going to talk about mostly in this presentation today, is the Canadian study. So that a year ago we had a certain amount of data we could present, and now here we are a year later. So there's a lot more data to share. So we'll go into that here. So Canadian story. So since 2007, we've been installing thousands of PCM Sluggers around the world, and for whatever reason, never made it to Canada until 2021. So just a couple years ago. But since 2021, we've installed. It says 185 here. All the numbers and the run life data in this presentation is based on the data collection that was as of September 29th. So September 19th, just over a week ago. So obviously now we've got an extra 9 days of data. So it's actually gone up to 190 installations now. But all the run life data we've got here is calculated as of September 19th. So we have 108, as of that date, there are 185 installations from 23 oil companies in 50 fields. Now, defining 50 fields, I'm sure there's some overlap in the names there just because different companies use different names for the same fields if they happen to be in the same area. But that's what we have in our records. So all over the place in Western Canada, from Medicine Hat in the south, the whole Lloydminster area, Edam, Saskatchewan, I think is the furthest east point that you see there, and all the way west to Peace River and north. So basically covering all the Western Canadian range of different types of oil, from cold heavy oil production with sand to some of the high water cut stuff that's down south, some more gassy applications, and to some very thick heavy oil up in the Peace River. So there's a huge range of different applications that we've seen over the last couple of years here in Canada. With we've been PCPs, standard PCPs, are producing these wells since 1980. Slugger is just coming in, but we're getting into that full range of these pumps. So we're seeing how they behave over that full range of applications. So just a quick summary of the results. We don't have production data for most wells. Pat's going to show you a few wells that we do have some production data for. As of, I think that the slides we've plotted there were from data collected back in June, so it's not completely up to date, but you'll get the idea. Of the 185 installations as of September 19th, 61 have been pulled, 41 have failed. Now, the data on this might not be perfect. It's entirely possible someone's pulled some pumps and not told us, so that's possible. It's also possible that some of these pumps that we don't know for sure if they failed or not. We get pumps that have been pulled with no data, So in general, on this, I'm assuming that if we don't know anything about it, it's failed. Obviously, the pumps that have tested fine, we're going to say they haven't failed. Mean time to failure calculated as per that SPE paper, which is basically total runtime divided by number of failures. If we look at all these 185 systems, total runtime, and then divide by 41 failures, we get 750 days. So that's what we're looking at here, which I think is pretty good. Just looking at that in a little more detail, a couple of different ways of looking at data. So the bottom graph is what's called a survival function, which basically shows you what percentage of pumps have lasted to a certain time. When you're looking at these graphs, when it starts to get really choppy there out at the end, it really has little value because there's just not enough data for it to be meaningful. But it's certainly, if you look at this, you go up to, say, 60% of the pumps have lasted 350 days. And that data is pretty reasonable at that point. So it's that, again, that's a pretty good run life, I think. The graph goes up to 629 days here. That was the last failure that we had. But there are 3 pumps currently running that have longer times than that. They're not on the graph because this graph ends at the last failure. So there's up to 820 days of runtime so far. The green graph at the top is showing the MTTF calculated in a 365-day window, so a 1-year window. So we're just looking at the most recent data. Now, we've only got a couple years of data here, so we're not showing a whole lot here. And the first half of this graph probably has a lot of uncertainty in it just because there aren't that many systems. But the last half is looking pretty good, and we're seeing MTTFs ranging 600 to 800, a little bit higher for a bit there. It was a period where we didn't have any failures, but 600 to 800 days of MTTF looks like where we're looking for the Slugger pump in Western Canada. So I'm going to let Pat talk about the 4 specific installations. Go ahead, Pat.
Thanks, Paul. So I guess in general, when we started this, you see the concentration is more around Lloyd. As we started to build these Slugger pumps, we had to get an inventory of rotors for 3 different elastomers, and everything takes time. So as we started going at the very beginning, what we got was the problem wells. So in very general terms, sand is a big issue in and around the Lloyd area, not so much now in the new horizontal completions, but we've got data backing 15 to 18% sand production. With that graph or chart you showed of all the wells, sand is being produced in a lot of these applications at lower percentages. Basically, what we're seeing in a lot of the cases is we're able to run lower RPMs. We see a better pump efficiency, and this is turning into some longer run times for us. The one thing that has pushed back on that is oil price, and every meter counts. So RPM, when we speed these wells up, if we're not seeing additional production, when we can slow them down, and in these cases, I'm talking to a lot of the operations people, we monitor that a little better than in general how things are going. Everybody is pushed for volumes. The other thing, reviewing failures, we do see a lot less heating and heat checking on the rotors, and a little bit higher percentage of stators coming in that can go back out. The lower temperature per stage gives us a bigger forgiveness window, and we're able to, where we are running with less fluid going through these pumps, we're seeing less damage, and the pumps can be rerun. We've got one customer that's questioned why we are getting less gas up through the tubing, and we have no real answer for that, other than we do know we move gas through the pumps better. The big thing is getting it in at the inlet. So if we are getting it in at the inlet after we do a service job, one of the possibilities is that we're not letting the gas build up. Therefore, the gas, they're seeing less gas push up through the tubing as well. So the case that's on the screen right now, this is up in the North Play. It now has 623 actual run days and is still producing. These wells are the Clearwater Play. They are very high gas volumes, and in general, a lot less sand production up there. So in this case, we went from 244 days, and we're basically at 623 days, and it's still producing. RPM in this case, we leveled it out at about 90 RPM, and we've been able to hold it, where the other pump in blue, they had ran it about 95 and jumped up to 140, trying to get right at the end of the pump's run life. The next slide is a well in Lloyd area here, where you can see the first few pumps. Again, it was one of their problem wells. It has really helped us with this customer. They were getting in that 30-day, 40-day run life, and we've been able to extend that runtime. Runtime on it is now, it's 531 days and still producing. The fluid has held consistent, and the operation staff have, this started out at about 50 RPM. They have slowly walked it up to 110 RPM and maintained a level line of production. So it's a great job of what operations can do. And in this case, they've really extended their run times. We have op costs on this well, which the service costs have reduced drastically, and it'll be interesting to see how long this one stays running. The next well is a 22 1800. So at the start, it was generally we got the problem wells. So after we had a few in the ground working discussions with our customers, I said, okay, if you've got a pump that a well that you're fairly happy with run times, and it's not a problem well per se, it's just your pumps are failing, let's go in there. So this well here, we are now at 586 days. So the first two runs, you're in that over 100 days and in the 200-day range. We've been able to triple that. The volume has stayed dropped down and stayed lower, and that's the case. Usually we start in as good or a little better on the efficiency than a regular pump, but off the hop, a lot of these wells do have some good production percentage or pump efficiencies. So this well, we have maintained an RPM of lower than 40 RPM. So that really helps us in the rod and tubing wear issues that we deal with as well. The next well is the longest running well we got, and so it is now at 828 run days. Again, it was a customer that was happy with the run times they were getting, or weren't happy, but they wanted a longer run time. But this wasn't a real problem well. It's just the run times were 160 to just under 300 days, and we have extended it to over 800 run days. The production again has dropped off, and it's held basically the same. Again, this well, we're running in that 50 RPM range, where the pumps before it were equivalent to us, or 80, and at the end of the life, they bumped it up to over 100 RPM. So we don't see the every application the same, but where we're able to get in and get the emulsion, the fluid into our intakes, we do see some really good extension on run times. That's it, Paul.
Okay, thanks, Pat. So just a quick summary of that with 4 examples that we have the production data for, with the 1 to 3 previous pumps in the same well, showing run life from 2 times to over 10 times, well over 10 times, I think, in one of those cases. That's pretty significant improvements in run life there. The efficiency that we see long term, 20 to 60% in those wells, suggests that the gas could be 40 to 80%. And that's just 100 minus 20 is 80, 100 minus 60 is 40. So the gas might be a bit less than that, but it's probably up in that range is what we're looking at for gas volume fractions. And yet these pumps are lasting quite some time. So that's again a quick summary of the Canadian experience on the PCM Slug over the last 2 years, the big years. So just the conclusion: the patented PCM Slugger is designed to, and I think significantly does, improve the run life of a PCP compared to the standard PCP in the same application. Thousands have been run worldwide, all over the world. Like I said earlier, Indonesia, Venezuela, the Middle East, Argentina, Colombia, Australia, a lot of them in Australia, pumping the coal seam gas there. And now in Canada over the last couple of years, showing, again, the same benefits that people have seen around the world. So just the summary, the Slugger provides insurance against the short run life in wells that have, or even might have. So even if you don't know if you're going to have gas, but if you think you might have gas, you can put the Slugger in because it doesn't hurt you. One thing we didn't show on here was efficiency. On a bench test, the Sluggers, so when there's no gas, the PCM Slugger basically has the same efficiency as the standard pump if it's sized properly for the application. So you're not losing anything by using the Slugger. They work just as well when there's no gas, when there is solids, viscous oil, water, whatever you're producing with a PC pump will go through the Slugger in the same way. We actually, I don't have slides for this, but it's on the surface transfer pumps as well. We've got some PCPs running surface transfer pumps in various places around the world, and we actually have the Slugger technology available on the surface pumps as well for when you've got gas going through them. So that's our presentation. The link that's on this page here is the video that I was showing at the beginning of this presentation. Again, it's just a introduction to the name Slugger from when we put that name on the HRPCP back in 2019. But at this point, I'm happy to open the floor to questions. Now, in this webinar, Teams webinar format, I haven't used this before, so bear with me as we try to make sure this works. But I think that I'm not sure if you can turn your own mic on or if I have to turn it on for you. So I see Evan has put his hand up, so let's try this. I'm going to go on here and allow microphone for Evan, and so you should be able to unmute. Okay, go ahead.
Yeah, can you hear me?
Yes, I can hear you.
Okay, I got 2 questions. The first one has to do with the location, size, what have you, of the hydraulic regulators. Is that standard for all applications, or do you fine tune that based on how much gas, for example, you're expecting?
No, it's sized based on the pump model. So it comes from the volume and pressure rating on the pump. So for one particular model of pump, it'll always have the HRs in the same place for that model. But it'll be different on a different model with a different volume and pressure rating.
Okay. Second question, you've had a lot of these come back for inspection now. Are you seeing any localized wear, pressure washing, what have you, at the location of the hydraulic regulators, or is it essentially indistinguishable from a regular one?
In general, I think the answer to that is not very much at all. I've seen one case where it was significant. So it's generally, out of all the thousands we've installed, I've only heard of one where that actually seemed to have caused a problem. So in general, no, it's not, pressure wash through those regulators has not been a problem.
Okay, thank you.
We have seen some wear around the shaved edges where you'll see the wear through the chrome and into getting close to base metal. That's on maybe 3 different pumps, but in general, we don't, and we see a way less heat checking on these rotors.
Cool, thank you.
Okay. Any other questions? Kevin, your hand is still up. That's okay. Sorry, Layden. Let's see if it's right. Let me find the control here to turn your. All right, you should be able to turn your microphone on now.
Yes. Good evening here from Kenya.
Hello, welcome.
Yeah, my question is generally about its installation. Is there any specialized kind of installation different from the normal PCP?
No, it's installed exactly the same way. The only difference on this is the rotor manufacturing has those hydraulic regulators, but when it's installed in exactly the same way as a standard PCP.
Okay, thank you.
I guess one thing I didn't mention earlier, for those who are interested, in terms of if you're using paddle rotors, we can combine that as well. We can put a paddle rotor and an HR on the same rotor. There's no problem with that at all. Okay, next question, Mohammed. Let me just allow your microphone. There you go. You should be able to turn your mic on now.
Hello, Paula. Hello, Patrick. How are you? This is Mohammed Sami from Egypt. Actually, I have 2 questions. The one which regarding the example which Patrick already showed before. Are these examples are considered the gas separator installation? For this, have you compared between the gas separators and the Slugger performance?
I'm sorry. Can you? Okay. Can you please repeat that? Sorry, it's something distracting me.
Yeah, it's okay. My question was regarding the example which Patrick has shown before between the conventional PCB and the Slugger ones. So have we compared the installing the gas separator, the conventional gas separator in this conventional PCB and the Slugger PCB? That was my first question. The second one, how could you determine the number of the flat pitches along the rotor? Is it considered in the design just one a flat and one conventional one, like the conventional rotor, I mean, or there is another factor should be considered while designing the rotor with these flat pitches?
Okay, let me just answer that second one first. The sizing and positioning of those is I guess the secret sauce to the PCM Slugger. So, we have the formulas and methods that our engineering group uses to design where those go. We're not publishing that information, so I can't share that with you. But that's the engineering know-how that goes into making these sluggers. On the first question, I know Pat can talk about what they've done in Canada. I'm not sure if they've run gas separators there. I know certainly in other places around the world, people have combined gas separators with the Slugger. And just again, works fine. Gas separators help in terms of reducing the amount of gas going through the pump, but if you've still got some that's coming through your gas separator, you can still use the PCM Slugger. I haven't seen specific comparisons with and without to be able to give you a comparison on that, but it's certainly something that I know people have done. I don't know, Pat, if you can add to that for Canada. Has anyone run gas separators with them?
Yeah, we've had discussions on it with a couple of different customers, and in the end, we have not combined the two. as of yet. It would be great to try one, and down
Yeah.
the road here, we probably will be able to, right?
Yeah, I know that in India, for example, it has been done for sure. I know that, and I think in Australia as well. But I don't have specific comparison data to show how well it's how the two things together work. Any other questions? So I see I just went into the chat, and that was Mohammed asking that question in the chat. So we've covered that one. Any other questions from anybody?
If anybody wants to see the Canadian case studies, they can get a hold of me, and I can get you copies. And that will show you the pump efficiency, the volumes being produced, and the RPMs that have been recorded as well.
Great. And now this since we've recorded this webinar, the Teams tells me it was recorded, so I expect we should be able to get this video and make it available so that your colleagues who weren't able to attend should be able to watch this video if they're interested. And certainly, again, if anybody has questions, if you don't feel like answering them or asking them in front of the group, feel free to contact me or Pat or any of your PCM representatives, and we'll be able to answer whatever questions you might have. So thank you very much for attending today. It's great to have so many people come out to this meeting, and I hope you have a great rest of your day. And again, if you have any further questions, just give us a call or send us an email, and we'll be happy to help you out. So again, thank you very much, everybody.